Hello everyone, and welcome to our session on logarithmic time complexity. Today, we'll explore how certain algorithms grow in performance with input size in a logarithmic manner. We'll cover the definition, see real-world examples, look at visual demonstrations, and discuss the advantages of logarithmic time complexity in algorithm design. Let's get started. Before we dive into logarithmic time complexity, let's quickly review what time complexity means. Time complexity measures the computational time an algorithm takes to run as a function of its input size. Algorithms can fall into various categories: constant, linear, logarithmic, quadratic, and so on. This concept is essential for analyzing and comparing how algorithms perform as the data they process grows. Now, let's focus on logarithmic time complexity, denoted as O, log n. This means that the running time of an algorithm increases logarithmically with the input size. In many cases, the base is 2, which we refer to as the binary logarithm. The key implication here is that even if the input size increases significantly, the number of steps only grows by a small amount. This makes logarithmic algorithms very efficient for large data sets. Several common algorithms exhibit logarithmic time complexity. For example, binary search efficiently finds an element in a sorted list by repeatedly having the search space. In balanced trees, such as AVL or red-black trees, operations like search, insert, and delete also run in O, log n, time. Additionally, some divide-and-conquer algorithms incorporate logarithmic steps in their processing. In the visual demonstration on this slide, you'll see an animation showing how binary search halves the search space at each step. Let's explore the mathematics behind logarithmic complexity. A logarithm answers the question, to what power must the base be raised to produce a given number? For O, log n, we commonly use base 2, log 2, n. For example, if n equals 1024, log 2, 1024, equals 10, meaning it takes 10 steps to reduce the problem size to a manageable level. This efficiency comes from the fact that each step reduces the problem size by a constant factor, usually by dividing by 2. Let's now build binary search to understand logarithmic BigONotation. So let's jump into the Visual Studio Code. I'm going to implement a program for binary search, which is a perfect example of a logarithmic time algorithm. We start by defining a function called binary search that accepts two inputs, a sorted vector of integers and a target value. The function's purpose is to locate the target within the vector and return its index. Inside the function, we initialize two pointers. Left is set to 0, the beginning of the vector. Right is set to the last index of the vector. We then enter a while loop that continues as long as left is less than or equal to right. In each iteration, we calculate the middle index, mid, using the formula. Int mid equals left plus, right left, /2. Compare the element at mid with the target. If the element at mid equals the target, we return mid. If the element is less than the target must be in the right half of the vector, so we update left to mid plus 1. Otherwise, the target is in the left half, so we update right to mid 1. If the target is not found, the loop exits and the function returns -1, indicating that the target is not present in the vector. Because binary search repeatedly halves the search space, its time complexity is O, log n, making it very efficient for large datasets. Let's execute it first. I'm trying to find number 15, which is not existing, and you will see that it returned the element not found. Now try to find number 7, and you will notice that it found at index 6 as array starts with 0. By defining and using the binary search function, we demonstrate an efficient searching technique that leverages a sorted array to quickly locate a target. The halving of the search interval in each iteration is what gives binary search its logarithmic time complexity, a classic example of an O, log n, algorithm. Now let's go back to presentation. Logarithmic algorithms offer significant advantages. Their efficiency is evident because they minimize the number of operations even when the input size is very large, making them ideal for scalable systems and real-time applications. However, it's important to note that many of these algorithms require preconditions such as sorted data or balanced data structures. If those conditions aren't met, the performance might degrade. Keeping these factors in mind is crucial when designing and implementing logarithmic algorithms. To summarize, logarithmic time complexity, or log(n), refers to algorithms where the number of steps grows very slowly as the input size increases. We've seen examples like binary search and tree operations, which demonstrate how even very large datasets can be processed efficiently. The takeaway is that logarithmic algorithms are essential for building high-performance, scalable systems. Thank you for your attention, and I'm happy to take any questions or discuss this topic further.